All right.
So welcome everyone to the October 24th Resource Management Working Group meeting. Apologies for those who are watching this in video who I am starting the meeting a little bit late, and so thanks for those who stuck around. And so we have one item on today's agenda. Ismo and Christian, feel free to talk through your CAP.
All right, so hello everyone, I'm Ismo Puusten, and do you see my screen?
Yep, it looks good.
All right. So briefly, this is about this. The CAP title is per quality of service class CPU affinity hints, and this is mostly about this AVX mitigation. There's a bug about or Kubernetes issue about AVX, and the idea there is that if we are running AVX workloads that are mixed with these regular workloads, then AVX will actually like push down the base frequency very easily, which then means that the non-AVX workloads are running slower. And the problem here is that it makes it, well, it's slower, and it makes it also like harder to kind of reason about the workload speed when these AVX workloads are running there too. So the core of the idea is that we want to split the AVX workloads and the non-AVX workloads so that they are not running on the same cores or sockets. So how we want to do this, and now when I say we, I mean these document authors, which are Connor Doyle and myself, Christian, and Alexander Kanevsky. So what we want to do is that we want to actually put the containers on certain CPU sets based on the pod quality of service class. So the idea is that we would have two new configuration values, the kubelet, which would be this best effort CPU set and other CPU set. And that would mean that these best effort pods would be limited to this PE CPU set, and the burst amount guaranteed pods would be running on the other CPU set. And by default, both of these CPU sets would actually be all CPUs, meaning that everything would run everywhere. And only if needed, then this would be kind of, system could be partitioned into smaller pieces. And there are some sort of side effects like this, that this allocatable quantity of CPUs needs to be calculated so that it's actually the smaller of all CPUs minus the reserved CPUs and the other CPU set, because that's where these CPUs where there is a CPU request go to. And then there are some examples, and the first variant is that these AVX workloads would be running as best effort workloads. So it means that everything else would have a CPU resource request on them, and so they would be running on this other pool, and only this AVX pods would run on this best effort pool. And that's sort of the kind of maybe the kind of the simplest like concept here. So just keep the workload separate. Then there are different extensions how this could be done, like this. For instance, to use a admission controller to modify the pod request so that if some pod had a label AVX, then it would have all these resources removed from it, which would then put it automatically to the best effort class. Then there's some other variants which are sort of simpler in that sense that they fix the AVX issue to some degree, but they don't require changes from Kubernetes, but they have some other issues then. For example, this variant 2 means basically that well, it's sort of the kind of the other way around. And if this AVX workloads are running as guaranteed pods, it means that this AVX workloads will actually land on their own kind of CPUs then. Especially with the static CPU manager policy, which means that if they actually are like these integer CPU requests, then they will have their own cores. And the algorithm goes even so that if there is like large enough request, then it will try to allocate first a full core, like both hyperthreads. And if it's even larger, it will then try to go to the full socket. Then the variant 3 is that we will do this, what Vish was suggesting when he was commenting on this KEP2, that we will just like sort of partition the whole cluster so that these AVX workloads are running only on some nodes, and only AVX workloads are maybe running on other nodes. But we say here that it can negatively affect cluster efficiency, which is sort of true, and it has some other side effects, like most likely people don't want to do it. We heard this from our customers that they are not sort of happy about this approach to this AVX mitigation. So they would rather split the nodes and not kind of or split the CPUs inside the nodes and not the nodes themselves. Then there is this another pending KEP about this ISO CPUs, and this sort of might actually help with that KEP, meaning that if you think of the set of all CPUs and then the best effort CPU set and then the other CPU set are just subsets of that, then the remaining CPUs outside of those sets, then they are sort of outside of the normal Kubernetes scheduling, which means that they are something very close to ISO CPUs. There are some implementation details, but maybe if there are now already some questions or comments about this, then would be happy to
So is the kubelet running in the other pool, just like every other best effort workload?
The kubelet? No, it's sort of running outside of this whole kind of this partitioning. The partitioning is sort of like internal only to the containers.
Are you envisioning creating anything to make it easier to manage the decision process around which CPU sets you set in either pool?
Yeah, this is actually a really good question, because that sort of comes down to the question that how exactly do these AVX workloads affect the frequency, the base frequency for these kind of non-AVX workloads. And that sort of depends on many things. For instance, I understand that it's different between different processors and so on. So probably there will be some tooling, maybe it's not done by us, but we do have some work that helps sort of the system administrators to analyze that, what sort of hit there would be. For instance, if you think of the kind of the cleanest separation of AVX and non-AVX workloads, then they are running on the different sockets, the whole different processors. But if they're running on the same processor, then what can we sort of expect there? What kind of performance changes? Then that sort of depends. Did that answer your question in any way?
Yeah, I guess what you've walked through thus far, it seems pretty clear at the low-level side. It's just how do we make the set of knobs digestible, I guess, is what I'm looking at on my side when reviewing this. So
yeah, of course, the kind of the sort of the ideal solution would be that you could actually adjust the CPU pools without having to restart the kubelet. But it's still sort of under investigation by us that what kind of restrictions exactly are there when you do this. Because I mean, the kind of the simplest solution is that if you want to adjust the CPU set sizes, let's say, then you just drain the node, adjust the CPU sets, and then sort of uncode on it again. But it could be that there are some operations or some adjustments which you could always make without having to do that. And which would mean that you just let the CPU manager kind of reschedule the pods to the CPU sets.
And then this might be obvious to some, but like what class of workload is best served by the introduction of this feature?
I'm sorry, say again.
What type of workload is a customer who's interested in using this feature running?
Well, it's typically like varied workloads, because the whole thing is a problem only when you have both AVX and non-AVX workloads running at the same time. Because I mean, AVX workloads are good in that sense that they actually they perform really well. And the only problem comes when you have these workloads running like mixed in the same node.
But I guess, is there a workload that's requiring them to be mixed in the same node versus creating node pools that are targeted for AVX versus non-AVX?
So it depends. I mean, I don't have any kind of concrete examples of what kind of workloads could be these kind of mixed workloads where there would be like two pods, because in order to have this quality of set classes, they're like pod level things. So you need to have two pods, one running AVX and one running non-AVX, which would need to be then scheduled on the same node. That's what you mean, I think.
Yeah.
But another case is just that you have, let's say, a public cloud where you have like a virtual machine on some particular computer. And then somebody else is running AVX workloads there. You don't even know about it. And he's being the sort of the noisy neighbor and actually like affecting your workload speed. So that's the other case. So these workloads may not come from the same source, but they just may happen to be running on the same node and affecting the other workload, like in the bad way.
But basically, as the cluster administrator, I had to understand that I had this class of noisy neighbor workload and pre layout a topology for my cluster that enables this to work as best.
Yeah, that's right. So, for example, you might require that the AVX workloads, if you actually know what they are, because this kind of presumes that this is kind of cooperative. So the AVX workloads actually are somehow like known to be AVX workloads. So there would be this label, or then there would be this convention that they are just the resources are set so that they go to these certain classes. And if you have, let's say, a label, then you can choose that these AVX workloads all go to these particular nodes, which are then split so that they have, let's say, certain.
Just so I understand the context a little better, is the noisy neighbor problem only when you have an AVX and non-AVX workload on the same node, or is it a problem to have two AVX workloads on the same node?
The problem is the real problem is when they are sort of different types. If they're both AVX workloads, then it shouldn't sort of affect, because the base frequency is anyway lower and the AVX is sort of just getting all the power. We are talking about sometimes about this kind of these dense AVX workloads when you're actually executing a lot of these AVX instructions on the same CPU. But that's not the problem in that case.
Can I say one comment related to this?
Sure.
So basically, actually, the situation is more complex because how the base frequency is affected, like Ismo told, how the base frequency is affected. is a function of several things. One of them is the SKU, so basically what type of CPU you're running on. But the other thing is what kind of AVX instructions you are running. And the third thing which affects it is that how many cores within the package are running AVX instructions. And one of the basic ideas of this cap is that by being able to limit the maximum number of cores that are executing AVX instructions within a node, you are able to sort of limit the downclocking effect to an accepted worst case for that node.
I guess
it is not.
What I'm struggling with is like there's this idea that the operator knows which workloads are using AVX versus not AVX, and they've steered their pods appropriately to take that into account. And then we're kind of contrasting that with this like, well, I could be running on a cloud and I'm kind of black box and I don't know anything about my end user workload, but I've pre-configured my nodes with these separate CPU set policies. Like, I guess I'm kind of wondering, like, if the consumer of this feature is a user who, like, I'm still hung up a little bit on why I would not just have dedicated node pools for one class of workload versus another, and what the major, like, if I'm sensitive to this issue, what the major workload requirement itself is that requires the two pods to be co-resident, like one that is and is not using AVX.
Yeah, I guess the splitting of the cluster into these AVX nodes and non-AVX nodes, it works too, so no problem about that, but it's just like sort of a maybe a bit easy solution because you can actually use that for any other things. So for example, why have extended resources for, let's say, GPUs, if you can just say that these are the GPU nodes and these are the non-GPU nodes.
Well, to have an extended resource for a GPU is useful so you can have a count of how many GPUs are schedulable in your cluster, and like the presence of a GPU extended resource on a node directs scheduling to that node. So whereas this, it's not quite the same. It's more like I have a very performance sensitive workload that takes advantage of AVX or is adverse to the usage of AVX, and I want to steer that workload to a particular node pool that is not impacted by that noisy neighbor effect you're describing. But it's not clear to me yet why or how or what class of user would say, I'm going to globally for my cluster configure my nodes to take advantage of the two working together by setting these policies appropriately. And this could be my own lack of knowledge, so I just apologize.
Okay, I have one comment related to this. So basically, if your AVX workload strategy is that you want to run AVX workloads on your cluster for so basically for the spare cycles. So you are putting them always into the best effort quality of service class. But you are having, like you told, sensitive workloads which are, for instance, running in the guaranteed QoS class and with the static policy enabled, so that you are having, so those are running with within dedicated cores. And those are sensitive, and you want to make sure that you can freely schedule. You do not need to set aside, for instance, time slots during the day when you can schedule your AVX workloads, but somehow you want to prevent them from severely affecting the performance sensitive ones. Then one option is that you are limiting how large number of cores within a node can concurrently execute AVX workloads. And by that, you are indirectly limiting the base frequency downscaling effect of the noisy neighbor AVX 500 workload. I don't know whether this clarifies. clarifies a little bit things further.
Yeah, the spare cycles is one, and one other possibility is that if you have like a specialized cluster, for instance, like a single node cluster, or a cluster that consists of like special nodes, which need to be performing many things because they happen to be somehow like special. Then you actually could run AVX workloads on those nodes too, if needed, while it wouldn't affect the other workloads there so much.
Okay, yeah, I guess that's why I was trying to figure out like what is the target admin for this specialized cluster who would take advantage of this, and it's very possible I'm underinformed on the target audience, I guess, that would be willing to create that cluster. I'm just looking at this from the perspective of it's easier to manage pools of nodes than to try to get fancier about managing partitioning within the node. And the CPU manager use cases we've explored previously were pretty clear to me on who the beneficiaries were. Like they were, whether it was DPDK or some other class of applications, like that was clear, I guess. And but in this particular case, who is not able to run a workload best on Kubernetes as it exists today, and in what use case environment with this issue with AVX is not as clear to me. And I apologize because, like I said, this is probably me just not speaking to the same user base that you guys are representing here.
Yeah, but that's a fair point, and I think for many users, just sort of like splitting up the cluster would work just fine. So I definitely agree with that. But I maintain that there are these special cases where it actually would be like beneficial to have this.
Yeah, so that's what I'm looking for, is like, what is the special case where the cost outweighs the benefit? I mean, where the benefits outweigh the cost, I guess. Is it like an edge appliance, Kubernetes in a box type case where you have some very particular intimate knowledge? Like that's what I'm just hung up a little bit on, is understanding what the special case is.
Yeah, for instance, we had recently this presentation by Levovar about this how they're running this edge equipment in the cell towers even which have these nodes which need to be doing many things at once. Then, for example, these kind of nodes might benefit from this. I can't give you any kind of this concrete like clusters that this is now definitely like somebody who will benefit from this, but we have understood that there are these people who would actually want to use this.
Okay, so basically it's a user who has a very fixed compute footprint, probably working in the edge, that needs to satisfy a disparate set of workloads as best possible with the greatest density on that fixed compute.
That's one, and then as Kristen mentioned, the spare cycles users are the other, which want to run these batched workloads without like having to sort of shut down entire nodes necessarily for that.
Okay, that's helpful to understand. Are there more areas you want to call out in the document here, or we can?
No, I think this was sort of the kind of the beef. Then we have this implementation details, and I have a small proof of concept implementing these, but I think these are kind of sort of secondary. I think the first question that I'm hoping to have this comments is that if this KEP is something that could actually like at some point be accepted, and what kind of changes or other ideas might come like regarding this whole AVX like mitigation issue.
The only other thing that struck me a little bit with this feature was we have a feature that Seth Jennings from Red Hat had started a while back called the Quaz Managed feature gate, which basically made it that, or what it aspires to do is make it that pods in lower quality of service tiers can't scavenge resources that were already reserved by pods in higher quality of service tiers. I feel like there's when you were first describing this, maybe a potential overlap between the two concepts. But after you've completed this, I'm not sure that thought in my head is as well thought out, but I guess as it pertains, like, is there anything unique to the NUMA stuff that you guys have presented, or how memory is managed that impacts what's done here or not done here?
No, not really. This shouldn't much affect that, except of course that this is also about like in the end this is about like pinning containers to certain CPU sets. But this doesn't really relate to the NUMA stuff that much.
I guess what I was thinking about was right now the Quaz Managed feature, if you look at it, basically protects against best effort pods from scavenging memory from burstable or guaranteed pods by setting the memory limit for the best effort C group tier, actually setting it, whereas typically it's unset, and setting it based on the sum of burstable and guaranteed pods on that node's request getting subtracted from what a best effort could use. And so if one of the things you were showing here was basically having a CPU set that was fixed that would just run best effort pods, what I guess I was wondering is if rather than fix that CPU set, you could make that CPU set just further restricting. But I guess that's kind of what the static CPU manager already does in practice by just moving non-guaranteed workloads to those other cores. And so if I was to compare like a user who's running the static CPU manager or not, the benefit of having a reserved set of best effort cores versus having the core set be restricted was that you could constrain the impacts of your noisy neighbor problem by restricting the number of cores that you offered as a guarantee. Is that how I understood it?
Yeah, that probably, or that might work, because this is, so indirectly this is trying to achieve the same thing, that you can put a cap on how many cores are concurrently executing AVX 512 instructions. So usually, so again, if you look at the details, in some cases it might matter which exact cores, I guess, because it's so complex, but I don't think there would be a significant. So I don't think you could come up with a workload or a configuration where you could show significant performance difference where two setups which only differ on which particular cores within the same package you are running the AVX 512 would end up significantly differently affecting the other non-AVX workloads on the CPU. So I think that maybe it would be enough to. So what you are suggesting, that instead of telling which particular cores, just say that how many cores can run AVX 512 workloads, maybe that could work.
Right, or just like turn on a static CPU manager policy and set cube reserved really high. And then impact would that be? Would be your guaranteed workloads would run in the integral CPU cores that you want to provide the right guarantee for. All your best effort workloads would run in that slush bucket. And would you not have the same basic effect as pre-reserving particular CPU sets for best effort?
Personally, I'm not sure, because now I have to admit that I don't. So I'm not sure whether.
Because that's what basically your best effort CPU set is doing, is it's acting as a reservation.
It's true that if I remember correctly, static policy, it only it doesn't sort of reserve the reserved set from the all CPU set, but it just is something that they make sure that it must be non-zero so that these other pods can also execute there. So it actually might work. Needs some
guaranteed ones are not going to execute there.
No, they are not.
Okay, well, I guess that's the set of feedback I would have looking at this initially, and maybe some of that feedback was good and useful, and maybe others of it is less so. But I want to thank you for presenting today, and I apologize for running late on starting the meeting. And we can bring this topic again up in a subsequent meeting where we can hopefully get some discussion and other folks giving their feedback after watching the video. So thank you, everyone. Is there anything else we wanted to cover for today? Otherwise, I'll give back the remainder of the time.
Yeah, thank you everybody for listening, and if you have any comments that I say this also to the potential video watchers, then just add them to the get PR as comments. Thank you very much.
All right, thank you guys. Bye everyone.
Bye.
Bye.